Welcome to ECE 302. This is lecture A.4 on autocovariance and independent random processes. I'm Professor Stanley. In the previous lecture, we talked about the autocorrelation function, the function of Rx at T1 and T2. The autocorrelation function tells us how a random process at certain time instant is correlated with another time instant. For example, if I have T1 here, I have T2 here, I'm looking at the random variable at T1 compared to the random variable at T2. These two, they are random variables because you have random realizations of the same random process. Like this one, you also have T1 and T2, and then you have different values. And if you look at the things vertically, or what we call it the statistical perspective, you can see that there is a random variable at T1, and then there is a random variable at T2. And therefore, we can talk about the correlation between x at T1 and x at T2. So this is the definition of the autocorrelation function. Now, we have also said that in the random variable case, you can talk about a pair of random variables, and then you can define what we call the covariance. The covariance is defined as the correlation minus the mean. So if we have mapped this autocorrelation function to this joint expectation of x and y, which is the correlation, then by subtracting the mean, we will be able to define something similar for this covariance function. So in this lecture, we're going to learn about this autocovariance. The second half of this lecture is the introduction of this independent processes, meaning that in what situation that you will get zero covariance. So let's talk about the autocorrelation function. The autocorrelation function of a random process x of t is defined as x at t1 minus mu x at t1 times x at t2 minus mu x at t2. Okay, so the way to understand this is to ignore this mu. Then what do you have? You have this expectation of x at T1, and then you have expectation x at T2. This is the autocorrelation function. Now, if you subtract mu1 and then you subtract mu2, when mu1 is mu at T1, mu2 is mu at T2, you multiply them 2, then you have this thing called the autocovariance function. The autocovariance function, as it is a generalization of the autocorrelation function, it is also a two-dimensional function in T1 and T2. And so any property that you will have from the autocorrelation function can be inherent to the autocovariance function. So let us try to prove two very useful properties of this autocorrelation function. The autocovariance function can be related to the autocorrelation function using this formula. The formula says that the covariance is written as the correlation minus the mean times the mean. The second property is that the autocovariance function, if you evaluate at t and t, with both t1 and t2 they are the same, you will get back the variance of a random function. So how do we prove the two results? Well, the two results are actually quite easy to prove. Let's look at the first one. The first one says that I want to look at this thing. It is the autocovariance function, t1 and t2. It is defined as the expectation of x at t1 minus mu1, and then I have x at t2 minus mu2. Now, this can be expanded to give you x at t1, x at t2, and then minus mu1 x at t2, and then you have minus mu2 expectation x at t1, and then you have mu1 and mu2. That's just the expansion of this equation. Then you recognize that this is nothing but Rx of t1 and t2. This is just mu2. This is just mu1. And then you have an addition of mu1 and mu2. So those two terms will give you 0. And so you only have the one term left. That is minus mu1 and mu2, which is this result. So we have proved the first statement. The second statement is also very easy to prove. You have t and t, and therefore you are really looking at this thing here. If you put this as t without the t1, without the t, this is just the random variable at t. Random variable, and this is the mean at t, and then they're the same. Of course, that will return you the variance. Okay, that's just the definition of this autocovariance function. So if you put in t and t, this will give you the variance of the random process. Okay, so let's look at two very quick examples. The first example is that you have a random process x of t. It is a times cosine 2 pi t, where a is distributed uniformly in 0 and 1. So what do we want? We want to find the autocovariance function. The autocovariance function, as we have defined, it is the autocorrelation function minus the mean. So what is the autocorrelation function? The autocorrelation function for this problem we have seen it multiple times. It is given by this 1/3 of cosine 2 pi t1 and cosine 2 pi t2. The mean of this function we've also calculated before. That is half of cosine 2 pi t1 and half of cosine 2 pi t2. So just plug these numbers in, then you take the difference, you will get to this 1/12 cosine 2 pi t1 and 1/12 cosine 2 pi t2. Now recognize that this is almost in the exact same form as this autocorrelation function. And therefore, what you would expect to see for this autocovariance function, so this is Cx of t1 and t2. It is a function of time t1 and time t2. You will have some pattern like what we have seen before. Okay, now this is not a very good drawing, but you know what I mean, right? So here you have the peak, and then you have the valley, and then you have the peak again. So remember those circles. This is the two-dimensional drawing of the autocovariance function, which is the same shape as the autocorrelation function for this problem. The other example is the autocovariance function. The autocovariance function for this phase problem is that you have this random phase theta here, where theta is distributed uniformly from minus pi to pi. And so we can calculate this autocovariance function, which is defined as the autocorrelation function minus the two means. What is the autocorrelation function? The autocorrelation function we have calculated in the previous lecture. This is given by 1/2 of cosine omega of t1 minus t2. The two mean functions we have evaluated 2 lectures ago. The mean functions of this random phase problem is 0. And so you're both 0 here. And then you can show that the autocovariance function is the same as the autocorrelation function. So if you draw the diagram, this is Cx of t1 and t2. You have t1 here, you have t2 here. You should have the same band structure as the autocorrelation function. So this is a tupeless structure. We can also define a thing called the cross-correlation function, where we change the variable. Instead of looking at x and x at t1 and t2, you can actually look at a pair of different random processes. So here your random processes are xt and yt. You can have x of t here, which is this function, and then you have yt, it is another function. You can talk about the correlation between this point and then the correlation between that point. So that would define you this cross-correlation function between two random processes. You have x at t1 and y at t2. Similarly, you can define the cross-covariance function, which is the covariance version of this correlation. Here you have x at t1 minus mu1, and then y at t2 minus mu at t2. And note that this is mean of y, this is mean of x. So a remark here is that the autocovariance function, the cross-covariance function, is the same as the cross-correlation function if the two mean functions they are 0. That also applies to the autocorrelation function. When it means they are 0, the covariance equals to the correlation. So I want to introduce another concept, which is the concept of independent random processes. Now I want to make it clear that independence is not just related to random variables. You can apply it to random processes as well. In random process, the way to define independence is somewhat complicated, okay? But we can actually try to understand a little bit. We say that the two random processes, x and y, they are independent if for any time instance, t1 through tn, this PDF is a joint PDF across time at t1, time through tn, and then y at t1 through y at tn. So this is a sequence of time instance. For x, the same sequence of time instance for y. You look at their joint distribution, that is the joint PDF. If you can factorize them into a product of these two, then you say that x and y are independent. Okay, so independent, what do you need? Independent means that f of x, y, this joint PDF can be written as x and y. Okay, that is the definition of independence. And for random processes, it's the same definition. However, you generalized it to an arbitrary number of timestamps. This n here can be arbitrary. It can be very, very big, it can be very, very small, but it has to hold for any timestamp t1 through tn. A very related concept to independence is the concept of uncorrelated. Uncorrelated says that the expectation of x at t1 and then y at t2, that can be factorized as expectation of x at t1 and then expectation of y at t2. Now, this is the definition of being uncorrelated. Note that the independence can imply uncorrelated. However, uncorrelated does not imply independence. Okay? Independence is a much stronger condition than uncorrelated. And so if you say that the two processes, they are uncorrelated by checking their expectation, it does not mean that the PDFs can be factorized. That applies to both random processes and also random variables. This is the formal statement that I'm making here, that if two random processes, they are independent, you can get uncorrelated. But if they're uncorrelated, you cannot go back to independent. And here is why. If you have two random processes, x and y, and then they have their own random indexes, psi and zeta, the way we define this joint expectation is to take x at t1 and y at t2 as two different random variables. You can take the joint expectation by putting the joint PDF. This is the way how we compute the joint expectation. Now, if the joint PDF can be factorized into a product of PDFs due to independence, then the double integration can be written as the product of two individual integrations, one using fx, the other one using fy. And therefore, you will have expectation of x, expectation of y. The reverse direction is not true, because if you have expectation being able to factorize, you cannot claim anything about whether the joint PDF can be factorized. Now, independent processes are extremely useful. It tells you when you can claim the correlation to be zero. If the two processes, they are independent, you will automatically get uncorrelated. And therefore, you can claim a lot of these joint expectations to be zero. That will simplify the calculations a lot. Here is one example. Let x and n be two independent random processes, and then I define y to be x plus n. I want to find the cross-correlation function between x and y at time t1 and t2. So, according to the definition of this cross-correlation function, it is defined as the joint expectation of x at t1 and y at t2. Well, what is y? Y is just x plus n, but now since I'm evaluating at t2, I just plug in the t2 here. So what is this? This is giving me the expectation of x at t1, x at t2, and then I have minus expectation of x at t1, and then n x at t1 and n at t2. So I have these two products. Okay, so you have x and x and n both at two different time instants. The first joint expectation is Rx at t1 and at t2. That is the definition of my autocorrelation function. The second expectation here, because x and n, they are independent, I can write it as the expectation of x at t1 times the expectation of n at t2. This is because independence imply uncorrelated, and therefore I can have this expectation to be factorized. And so once you have this expectation of x1 and expectation of n, you know that this is just mean of x at t1. This is just mean of n at t2. And therefore you can show the final result, which says that the cross correlation between x and y at t1 and t2 is the autocorrelation function of x times the individual mean functions. Alright, so we have introduced a couple new concepts here. The first one is the autocovariance function, the Cx of t1 and t2. The second concept that we introduce here is the cross correlation x and y, t1 and then t2, as well as cxy, t1 and then t2. So these are the cross correlation and also the cross covariance functions. And finally, we define this notion of independence, because independence imply uncorrelated, but then uncorrelated does not imply independence. For independence to hold, you need to separate the joint PDF. For uncorrelated, you only need to have the two random variables. When you take the joint expectation, they can be separated. And this notion applies to random processes as well. Okay, so I hope you have learned something today. If you have any question, please let me know. These are very basic ideas for random processes, and we will use these concepts very often throughout our course. So please let me know if you have any question, and please also work on your homework problems. I will see you next time. Thank you.